Deep beneath the silent precision of our best atomic clocks, something astonishing is ticking in sync with the most destructive objects in the universe. Black holes and atomic clocks are mysteriously connected through the very nature of time itself. By the end of this journey, you will understand how these cosmic monsters shape reality in ways that challenge everything we thought we knew. We will explore how time stretches and warps, how gravity whispers to atoms, and what secrets this reveals about the fabric of the cosmos. How does a supermassive black hole billions of light years away influence a clock in a lab? Why do the rules of the very small and the very large seem to speak the same hidden language? What do you believe is the true nature of time? This is the single most important idea you need to grasp. Time is not a river flowing at the same speed for everyone. It is more like a landscape with hills and valleys created by gravity and motion. The stronger the gravity, the deeper the valley, and the slower time flows within it. This is not science fiction. It is a proven fact of our universe, predicted by Albert Einstein over a century ago. His theory of relativity showed us that a clock placed at sea level, where Earth's gravity is slightly stronger, will tick just a tiny bit slower than an identical clock placed on a mountaintop. This effect is called time dilation. We have measured it. Our GPS satellites must account for it because their atomic clocks, orbiting high above the planet in weaker gravity, actually run faster than the clocks on the ground. If engineers did not constantly correct for this, your navigation system would guide you into a field within minutes. So the very tools we use to map our world are directly affected by this warping of time. This proves that the connection between gravity and time is not some abstract theory. It is a real, physical phenomenon that we live with every day. Now, take this concept and push it to its absolute extreme. What is the most intense gravitational field imaginable? A place where gravity is so powerful that not even light can escape its pull. This is the domain of the black hole, where the valley of time becomes an infinitely deep well. But to truly appreciate this cosmic conversation, we need to understand the other partner in this dance, the one that listens for gravity's faintest whispers. That partner is the atomic clock. It is not a clock in any conventional sense with gears and pendulums. It is a device of almost unimaginable precision, counting the seconds by watching atoms themselves. At the heart of these machines are atoms like cesium or rubidium. These atoms have a natural, internal rhythm, a vibration that is incredibly stable and constant. Think of it like a tuning fork that rings with a perfect, unchanging pitch. But this tuning fork is an atom, and its pitch is so high it vibrates billions of times every single second. An atomic clock counts these vibrations. For a cesium clock, it counts exactly 9,192,631,770 oscillations to define one single second. This is not an estimate. It is the international scientific definition of a second. This incredible stability means these clocks are the most accurate timekeeping devices humanity has ever created. They would not gain or lose a single second for millions of years, but their true magic lies in their sensitivity. Because they measure time so perfectly, they can detect the most minuscule changes in its flow. They can feel the subtle tug of gravity from a change in elevation of just a few centimeters. They can hear time speed up when moving at highway velocities. They are the ultimate proof that Einstein was right because they measure the effects he predicted with breathtaking accuracy. These clocks are not just laboratory curiosities. They are the silent, beating heart of our modern world. Every GPS satellite in orbit carries an atomic clock. Your phone's map application relies on the signals from these clocks to triangulate your position. The entire global financial network is synchronized by them. They are essential for scientific research, from tracking deep space probes to searching for the mysterious dark matter that permeates the cosmos. They are our bridge, our sensitive instrument that allows us to take the mind-bending rules of the universe, written in the language of relativity, and measure them right here on Earth. They turn abstract theory into tangible, ticking reality. This intense warping of spacetime makes a black hole the ultimate time machine, a natural laboratory for the most extreme physics imaginable. At the edge of a black hole lies its point of no return, a boundary known as the event horizon. Cross this invisible line, and the gravitational pull becomes so overwhelming that escape is impossible. But the effects begin long before you reach that final threshold. As you approach a black hole, the gravitational field becomes so powerful that it begins to stretch time itself. Imagine watching a spacecraft fall toward a black hole from a safe distance. You would see its signals slow down, its movements become glacial. The clocks on that ship, from your perspective, would tick slower and slower until they seemed to almost stop completely at the very edge of the event horizon. For the brave astronaut on that ship, however, their own clock would appear to tick normally. Their personal experience of time would be unchanged, but the universe outside would appear to speed up, stars wheeling across the sky in a frantic blur. This is time dilation pushed to its absolute limit, a direct and terrifying consequence of Einstein's genius. What does this tell us? It proves that time is not a universal constant. Its rate is dictated by the environment, by the gravitational landscape it exists within. And at the edge of a black hole, that landscape is the steepest slope in the entire cosmos. Einstein's theory of general relativity gave us the mathematical language to describe this cosmic slowdown. It tells us that gravity does not just pull on objects, it pulls on time itself. The presence of mass or energy warps the very fabric of spacetime, and this curvature is what we experience as gravity. A clock placed in this warped region has to tick more slowly because the path it takes through time is literally stretched. This is gravitational time dilation, a direct and unavoidable consequence of how our universe is built. We do not just see this near black holes, we have measured it right here on Earth. In a famous experiment in 1971, scientists flew atomic clocks on commercial jet airplanes. After the flights, they compared those clocks to others that had remained stationary on the ground. The traveling clocks, having experienced slightly less gravity, were ahead by a few hundred billionths of a second. The math from Einstein's theory predicted the exact difference. This was not a minor success. It was a stunning confirmation that the rules governing the cosmos also apply to our everyday reality. Now, amplify that earthly experiment to an unimaginable degree. Place one clock near a black hole's event horizon and another far away in empty space. The difference would not be billionths of a second. From the perspective of the distant clock, time for the clock near the black hole would appear to have nearly stopped. Centuries could pass in the universe while only moments tick by at the edge of the abyss. This is the ultimate expression of the same principle, proving that the precise ticking of an atom and the destructive gravity of a black hole are bound by the same fundamental rule. They are speaking the same language, a language written in the geometry of spacetime. Yet these two worlds, the immense and the infinitesimal, speak to each other. The language they share is the flow of time, a rhythm that connects a black hole's gravitational grip to an atom's perfect vibration. This conversation hints at a far greater mystery, one that has puzzled physicists for a century. We have two magnificent theories that explain our universe. General relativity describes the force of gravity and the large-scale structure of cosmos from planets to black holes. It is a theory of the smooth, warping fabric of spacetime. Quantum mechanics describes the bizarre and probabilistic world of atoms and particles. It is a theory of discrete packets and fuzzy probabilities. Both are spectacularly successful in their own domains, but they are fundamentally incompatible. They speak different mathematical languages and obey different rules. Where gravity is strong and spacetime is sharply curved, like at the center of a black hole or the moment of the Big Bang, our physics breaks down. We simply do not know how to combine them. This is the single greatest unsolved problem in fundamental physics, the quest for a theory of quantum gravity. And this is where our two characters, the black hole and the atomic clock, step onto the stage together. They are not just a curious coincidence, they are a bridge. The atomic clock is a quantum device. It measures time by observing the quantum jump of an electron between energy levels inside an atom. Its incredible precision comes from the rules of the quantum world. The black hole, according to the best ideas we have from Stephen Hawking, is not completely black. It should slowly evaporate by emitting quantum particles, a process that ties its immense gravity directly to quantum mechanics. Their synchronicity, the way they both dance to the same tune of time dilation, suggests they are both touching a deeper, unified truth. By studying how gravity affects the quantum ticks of an atomic clock with ever greater accuracy, we are essentially conducting a real-world experiment in quantum gravity. We are probing the edge of our knowledge, searching for any tiny deviation, any subtle whisper that Einstein's theory might need a quantum correction. Each improvement in these clocks brings us closer to hearing that whisper, to finding the key that will finally unlock the universe's deepest secret and unite its two greatest theories into one. The evidence for this cosmic conversation began not in deep space, but in the cargo holds of commercial airliners. In 1971, physicists Joseph Hafele and Richard Keating performed an experiment that would become legendary. They placed supremely accurate atomic clocks aboard scheduled passenger flights that traveled around the world. These were not special research jets, but ordinary planes carrying ordinary people, with a few extraordinary timepieces stowed in the cabin. After the journeys were complete, they compared the clocks that had flown to identical clocks that had remained securely in the laboratory. The results were undeniable. The traveling clocks had not kept perfect time with the stationary ones. They were off by precisely the amount that Einstein's equations had predicted. The clocks that flew at high altitude in a slightly weaker gravitational field and at high speed had experienced time differently. They had gained a few hundred billionths of a second. This was not a theoretical calculation or a thought experiment. This was a direct, measurable proof that the flow of time is malleable, changed by both motion and gravity. It was a stunning validation of relativity using the most mundane of settings. Decades later, scientists pushed this precision even further. They placed one atomic clock on a laboratory floor and another on a table just a meter higher. And they measured the difference. The clock on the table, a mere 3 feet farther from Earth's center of mass, ticked imperceptibly faster. They could detect time speeding up over the height of a coffee table. These are not abstract concepts. They are physical realities we can measure with astonishing accuracy, all thanks to the quantum heartbeat of an atom. Each of these experiments is a milestone, a point on a map that connects our world to the most extreme environments in the universe. They demonstrate that the same rules that govern a clock on a jet plane also govern time at the edge of a black hole. The atomic clock is our translator, making the whispers of the cosmos audible right here on Earth. This dramatic slowdown is not an illusion. It is a fundamental property of reality for anyone observing from a safe distance. If you could watch a star collapse into a black hole, you would witness its final moments stretch out over an eternity. The light from its surface would redden and fade, seemingly freezing at the moment of its disappearance behind the event horizon. For the universe at large, the formation of the black hole is a process that never quite finishes, its final act playing out in infinitely slow motion. This has profound implications for how we understand these cosmic objects. We are not seeing them as they are in a present moment, but as they were in a deeply warped past, their signals heavily distorted by the extreme gravity they generate. Their influence on spacetime is so complete that they sculpt the flow of time itself in their vicinity, creating a kind of permanent shadow in the chronology of the cosmos. And while we cannot place a clock near a black hole, we have created the next best thing right here on Earth. Our most advanced atomic clocks are so sensitive that they can measure the minuscule time dilation caused by a change in height of just a few centimeters. By studying these tiny, precise distortions in the flow of time within our labs, we are effectively creating scaled-down simulations of these immense gravitational fields. We are learning the grammar of gravity's language, one perfectly measured tick at a time. This astonishing sensitivity transforms a simple timekeeper into something far more profound, a direct sensor of gravity itself. Because these clocks measure the flow of time with such incredible accuracy, they are effectively measuring the strength of the gravitational field they are sitting in. A faster tick means weaker gravity, a slower tick signals a stronger pull. This principle allows scientists to use networks of these clocks as a global web of gravity detectors. By comparing the tick rates of clocks in different locations, even at slightly different elevations in the same lab, researchers can map the most minuscule variations in Earth's gravitational field. They can detect underground caverns, shifting magma chambers, and even the changing mass of polar ice sheets, all by watching time itself speed up or slow down by vanishingly small amounts. This is not just a laboratory trick, it is a powerful new way of seeing our planet, but the implications reach far beyond Earth. The same time dilation effect that a clock experiences when lifted a few centimeters on a table is identical in nature to the effect a clock would experience near a black hole. The only difference is one of unimaginable scale. Our most precise atomic clocks here on Earth are experiencing a gravitational environment that is, in a mathematical sense, a tiny, scaled-down version of the immensely warped spacetime near a cosmic monster. By studying how these clocks behave in our planet's gentle gravity well, we are running a controlled experiment on the very physics that governs the most extreme regions of the universe. We are using the predictable, measurable ticks of atoms to decode the violent, chaotic warping of spacetime around a black hole, turning these quantum machines into proxies for exploring the abyss. This foundational research is already bleeding into transformative technology. The same principles that allow an atomic clock to sense gravity are the bedrock of gravitational wave astronomy. When a gravitational wave, a ripple in spacetime from a cataclysm like two black holes colliding, passes through the Earth, it minutely stretches and compresses space itself. This incredibly tiny distortion temporarily changes the distance between objects, and by extension, the travel time of light. Observatories like LIGO use lasers bouncing down long tunnels to detect this change, effectively using the speed of light as an ultra-precise ruler. But the next generation of detectors may instead use the unwavering rhythm of atomic clocks as their ruler. By synchronizing clocks placed kilometers apart and monitoring how the tick rates change relative to each other as a wave passes by, we could open an entirely new window onto the cosmos, listening for the faintest echoes of distant collisions. The atomic clock, born from quantum mechanics, is becoming our most versatile tool for listening to the gravitational symphony of the universe. This incredible sensitivity all comes down to a single, perfect rhythm. At the core of every atomic clock is an oscillator tuned to the specific frequency of an atomic transition. Think of it like finding a note so pure and stable that the entire universe hums along with it. For a cesium atom, that note is the frequency it emits when an electron jumps between two specific energy levels, a vibration that occurs exactly 9,192,631,770 times per second. This is not just a number. This frequency is the official definition of the second, the bedrock of all modern timekeeping. The clock's entire purpose is to lock onto this atomic frequency and count its cycles with flawless precision. It is this unwavering quantum mechanical rhythm that makes the clock so powerful. But according to Einstein, this perfect frequency is not immune to gravity's influence. The gravitational potential, which is simply the strength of the gravity at a given location, directly affects the flow of time. And since frequency is just the number of events happening in a specific interval of time, a change in time's flow must cause a change in frequency. If time slows down, everything slows down, including the vibration of atoms. So, an atomic clock placed in stronger gravity will have its fundamental frequency shifted ever so slightly lower. Its perfect note will flat. Conversely, in weaker gravity, the frequency shifts higher, the note sharpens. This is the critical link. The atomic clock does not just measure time. It measures the gravitational field by detecting how that field warps the frequency of light itself. This is the phenomenon harnessed in every precision measurement. By monitoring the stable frequency of atoms in one location and comparing it to another, we are directly reading the gravitational landscape. A difference in their tick rates is a direct measurement of a difference in gravity. This is why a clock on a table ticks faster than one on the floor. It is why a clock on a mountain runs fast compared to one at sea level. The frequency standard is reporting back on the shape of spacetime it is sitting in. Now extend this principle from our gentle Earth to the crushing gravity near a black hole. The same rule applies, only the effect is magnified to an almost unimaginable degree. The incredible gravitational potential at the event horizon would cause the frequency of an atomic clock to redshift into almost nothingness. Its steady tick would slow to a near standstill from our distant perspective. By studying how these ultra-stable frequencies change here on Earth, we are learning to interpret the extreme redshift we observe from matter falling into distant black holes. We are using the predictable quantum rhythm of atoms in a lab to decode the violent gravitational symphony of the cosmos. This direct link between frequency and gravity is the key that unlocks a new way of listening to the cosmos. When two black holes spiral inward and finally collide, they do not create a silent explosion. They send a powerful shudder through the very fabric of spacetime itself, a ripple known as a gravitational wave. These waves are not made of matter but of pure geometry, stretching and compressing everything in their path as they travel outward at the speed of light. When one of these waves passes through you, it minutely changes the distance between your left and right sides. It is an incredibly tiny effect, far smaller than the width of a single atom, but it is real. And crucially, it also changes the flow of time. As the wave stretches space, it also dilates time, causing clocks to momentarily tick slower. When it compresses space, time contracts and clocks tick faster. This means a gravitational wave is not just a ripple in space, but a ripple in time itself. For decades, we have detected these waves using enormous laser interferometers like LIGO, which measure the physical stretching of space over kilometers-long distances. But what if we could instead listen for the wave's effect on time? This is where the atomic clock enters the story once more. A network of these ultra-precise clocks, spread across the globe or even across the solar system, could act as a fundamentally different kind of observatory. As a gravitational wave passes by, it would ever so slightly alter the tick rate of each clock in the network at slightly different moments. By comparing their rhythms, looking for a telltale signature of time being stretched and then compressed in a specific pattern, we could directly hear the wave's temporal fingerprint. This would open an entirely new window onto events like black hole mergers, allowing us to study them not just by how they bend space, but by how they warp time. The same quantum technology that defines a second on Earth could become our most sensitive ear for the echoes of cosmic violence billions of light years away, proving that the language of relativity speaks equally in the lab and in the void. This relentless pursuit of precision is not just about building better clocks. It is a direct assault on the deepest questions in physics. These machines are the ultimate testing grounds for the fundamental laws of our universe. At their heart lies a profound question. Are the constants of nature truly constant? Is the fine structure ratio that governs the strength of electromagnetic interactions always the same everywhere? Does the mass of an electron change over billions of years? Atomic clocks are so stable that they can be used to hunt for the answers. By comparing the tick rates of different types of atomic clocks over long periods, scientists can search for any tiny, gradual drift in the fundamental constants they rely on. It is like using two incredibly precise rulers made of different materials to see if one of them is secretly shrinking. A detectable drift would be a monumental discovery, revealing that the very bedrock of physics is not fixed, but shifts over time or changes in different parts of the cosmos. This would force a complete rewrite of our understanding of reality. Furthermore, these clocks are continuously putting Einstein's theory of relativity through its paces. Every time a clock is moved, its tick rate changes exactly as predicted. This is a relentless verification of the theory's core principles. But physicists are now pushing this further, searching for any minuscule deviation from Einstein's predictions. Could there be a crack in the theory's foundation, a tiny discrepancy that only appears under the most precise measurements? Finding such a flaw would be even more exciting than confirming the theory, because it would point the way toward new physics, toward the holy grail of a unified theory that reconciles gravity with the quantum world. By placing these exquisitely sensitive quantum devices in different gravitational environments, from lab floors to mountaintops to orbiting satellites, we are essentially recreating the extreme conditions near a black hole in a controlled, measurable way. We are probing the edges of our knowledge, using the steady heartbeat of an atom to listen for the faintest whisper of a deeper truth waiting to be discovered. The universe keeps no single time. Its grand clock is a chorus of countless different tempos, each one dictated by its local environment. From our gentle planet to the crushing depths of a black hole, the flow of time is a variable and deeply personal experience. This is not a philosophical idea. It is a physical reality, and we can now map it thanks to the incredible sensitivity of atomic clocks. These devices provide us with a cosmic perspective, allowing us to understand how time itself is woven into the fabric of the universe. By comparing clocks across the globe and in space, we are creating a detailed chart of time's flow, revealing the subtle hills and valleys in the landscape of space-time created by Earth's own mass. This map shows us that time speeds up on a mountain and slows in a valley, a direct and measurable echo of the same physics that governs the cosmos. This understanding transforms our view of reality. Time is not a backdrop against which the universe plays out. It is an active participant shaped by matter and energy, and in turn shaping how everything unfolds. Nowhere is this more extreme than near a black hole, where time distortions reach their absolute limit. Here, gravity warps time so severely that it influences the very paths that light can travel. Particles are forced into strange new behaviors, and the fundamental rules of cause and effect are stretched to their breaking point. To understand a black hole is to understand the ultimate expression of time's variability. By using our atomic clocks to study these subtle effects on Earth, we are developing the language to interpret the violent distortions we see across the universe. Each precise tick from a lab brings us closer to comprehending the profound role these cosmic engines play in sculpting the geometry of spacetime itself, reminding us that the rhythm of an atom and the gravity of a singularity are two verses of the same cosmic song. This reliance on relativistic timekeeping is not a mere technical footnote. It is the absolute foundation of the global positioning system. Every single GPS satellite orbiting high above the Earth carries multiple atomic clocks on board. Their job is to continuously broadcast the exact time along with their precise location. Your phone or car's GPS receiver picks up these signals from several satellites at once. Since the signals travel at the speed of light, your device can calculate its exact position on Earth by measuring the minuscule differences in how long each signal took to arrive. It is a continuous, high-stakes triangulation based entirely on the precise measurement of time. But here is the crucial part. The atomic clocks on those satellites are flying through a different region of spacetime than your phone on the ground. According to Einstein, two effects are constantly at play. First, special relativity says that because the satellites are moving at high orbital speeds, their clocks should run slower relative to clocks on Earth. Second, general relativity says that because they are farther from Earth's gravitational pull, their clocks should run faster. These two effects do not cancel each other out. The gravitational effect wins, meaning the satellite clocks gain about 38 millionths of a second every single day. That might sound tiny, but at the speed of light, that error translates into a positioning mistake of over 6 miles per day. Without the built-in software that constantly corrects for Einstein's predictions, your map application would be utterly useless within minutes. Your navigation system is, therefore, a daily and practical application of relativity, a technology that only works because we understand how black holes warp time. This is not abstract physics, it is in your pocket right now. As we look to the future, this principle becomes even more critical. Navigating a spacecraft near a massive planet like Jupiter, with its immense gravity, would require even more precise time dilation corrections. And looking even further, one can imagine a future where spacecraft might use the predictable time warping around a gravitational extreme as a kind of cosmic lighthouse. By measuring the subtle shifts in the tick rate of an onboard atomic clock, a ship could infer its position relative to a neutron star or even a black hole, using the gravity well itself as a navigational marker. The same physics that makes these objects so destructive could one day become the guideposts for the most ambitious journeys through the cosmos. These theoretical predictions push the very boundaries of what we believe is possible. Some of the most compelling ideas come from the work of Stephen Hawking, who theorized that black holes are not truly black. Due to quantum effects occurring right at the edge of the event horizon, they should slowly leak a faint glow of particles, now known as Hawking radiation. This evaporation process is unimaginably slow for a large black hole, but it signifies a profound connection between gravity, quantum mechanics, and thermodynamics. The existence of this radiation implies that a black hole has a temperature, and anything with a temperature must influence its surroundings. This leads to a startling possibility. The quantum vacuum around a black hole is not still and silent. It is a seething sea of virtual particles popping in and out of existence, and the black hole's immense gravity dramatically energizes this quantum foam. These vacuum fluctuations could, in theory, create subtle ripples that propagate through the fabric of spacetime. While these ripples would be far too faint to detect directly across cosmic distances with today's technology, their cumulative effect might imprint itself on the one thing we can measure with godlike precision, the flow of time itself. This is where our atomic clocks re-enter the story. Theorists suggest that these distant cosmic events could induce minuscule, measurable shifts in the fundamental frequencies that atomic clocks rely on. It would be an effect so small that it would be drowned out by nearly every other force on Earth, from the rumble of a truck passing on a distant highway to the subtle shifting of tectonic plates. But as our clocks become ever more precise and stable, we are building instruments sensitive enough to potentially listen for this whisper. Imagine a future network of clocks, perhaps placed in deep underground laboratories or even on the moon, isolated from earthly vibrations and synchronized to act as a single planet-sized ear. By comparing their ticks, scientists could search for a synchronous global drift in time, a signature that cannot be explained by any local phenomenon. Such a signal would be the smoking gun, evidence that a cataclysmic event in a distant galaxy, or the steady hum of a supermassive black hole, is subtly tuning the rhythm of reality everywhere. This is the grand motivation driving this field forward. We are no longer just testing Einstein's theory. We are using the quantum regularity of atoms to hunt for the ghosts of quantum processes at the edge of spacetime, searching for proof that the universe is even stranger and more connected than we ever dreamed. Detecting this cosmic conversation is a monumental task of precision. The effects we are searching for are almost unimaginably small, buried deep within a universe of noise. Consider the challenge of measuring a shift in time so tiny that it is equivalent to a single second lost over the entire age of the universe. Now try to measure that on a planet that is constantly vibrating with earthquakes, weather, and human activity. The rumble of a distant train, the subtle pressure change from a passing storm, even the thermal expansion of the clock's own components from a ray of sunlight, all of these can drown out the faint signal we are trying to hear. Isolating a clock from this cacophony is the first great hurdle. Scientists place them in deep underground bunkers, suspend them on advanced shock absorbers, and encase them in multiple layers of vacuum and cooling, all to create a bubble of perfect stillness in a restless world. But even this is not enough. The next challenge is the clocks themselves. While today's best atomic clocks are miracles of engineering, we need them to be even better, 100 times, 1,000 times more precise and stable to have any hope of detecting the universe's quietest whispers. This relentless drive for perfection is fueling a revolution in timekeeping, moving from microwave clocks based on cesium to a new generation of optical clocks. These devices use atoms like ytterbium or strontium, which vibrate at frequencies 100,000 times higher than cesium, in the range of visible light. This is like moving from counting the ticks of a grandfather clock to counting the individual vibrations of a guitar string that has been plucked. The higher frequency provides a far more precise ruler for measuring time, promising accuracies where a clock would not lose a second for tens of billions of years, longer than the current age of the universe itself. Yet even with such a perfect instrument on Earth, we face the ultimate limitation of distance and inaccessibility. We cannot travel to a black hole to place a clock beside it. We are forced to observe them from across cosmic gulfs of millions of light years, interpreting their faint, redshifted signals as they were in the distant past. This forces us to become cosmic detectives, piecing together clues from immense distances with instruments of breathtaking sensitivity, hoping that the subtle story they tell here in the lab is the same story written in the violent heart of a galactic core. These quiet laboratories on Earth are merely the beginning of the hunt. The next great leap in this cosmic investigation will take place not in underground bunkers, but in the pristine silence of space. Several ambitious missions are being prepared to lift our most precise atomic clocks above the atmosphere, freeing them from the noisy vibrations and magnetic fields of our planet. One such project is NAS, a deep space atomic clock, a technology demonstration that has already proven its remarkable stability in orbit. This Mercury ion clock is a precursor to a new generation of timekeepers designed for interplanetary travel. Its core purpose is to enable autonomous spacecraft navigation. Instead of relying on signals being bounced back to Earth for calculation, a future probe carrying such a clock could calculate its own position in real time by comparing its internal, ultra-stable time with signals received from Earth. This is like giving a spacecraft its own perfect sense of rhythm, allowing it to sail the solar system with unprecedented independence, but the scientific potential runs far deeper. A clock operating in the stable environment of deep space becomes an unparalleled sensor for testing fundamental physics. It could measure the gravitational time dilation of the Sun with new precision, or listen for the faint ripples in spacetime from distant cosmic events with a clarity impossible to achieve on our trembling planet. By placing these quantum devices in the void, we are building the most sensitive ears yet for the universe's subtle whispers. This quest for silence and stability is driving us toward a new era of quantum timekeeping. The next generation of clocks no longer relies on the microwaves that power traditional cesium devices. They have moved into the realm of light itself. Optical atomic clocks use lasers to probe atoms like strontium or ytterbium, which vibrate at frequencies hundreds of thousands of times higher. This is a monumental leap in precision. Where a cesium clock counts the oscillations of a pendulum a few centimeters long, an optical clock counts the vibrations of a pendulum so small it is measured in nanometers. Their potential accuracy is almost incomprehensible. One of these clocks would not gain or lose a single second over the entire current age of the universe. They are not just timekeepers, they are the most precise scientific instruments ever constructed by human hands. Their incredible sensitivity makes them perfect for an audacious new mission. To listen for the faintest echoes of black holes themselves, theorists propose that the quantum vacuum around a black hole is not empty, it seethes with activity. Virtual particles flicker in and out of existence, and the black hole's immense gravity can tear these particle pairs apart, giving one enough energy to escape as real radiation. This is Hawking radiation, the theoretical glow that causes a black hole to slowly evaporate over eons. This process is not silent. It is a quantum storm raging at the event horizon, and it could create subtle ripples in the fabric of spacetime. These ripples would be immeasurably faint by the time they cross the cosmos to reach us, but they might leave a trace. They could cause minuscule, synchronous shifts in the fundamental frequencies that all atomic clocks rely on. It would be a whisper buried under a mountain of noise, a signal so small that today's best instruments would never hear it. But tomorrow's optical clocks, especially if networked together across the globe or placed on the quiet surface of the moon, could be sensitive enough to detect this universal drift. They could act as a single planet-sized antenna tuned to the frequency of spacetime itself. By comparing their flawless rhythms, scientists could search for a signature that has no earthly explanation, a gentle sigh from a distant abyss that subtly tunes the rhythm of reality everywhere at once. This is the ultimate goal, to use the quantum regularity of atoms here on Earth to eavesdrop on the quantum chaos at the edge of a black hole, proving that these two worlds are intimately, undeniably connected. This profound warping of time transforms a black hole into nature's ultimate time machine. The effect is not magic, but pure physics. An astronaut orbiting just outside the event horizon would experience time passing at a dramatically slower rate compared to everyone else in the universe. For them, a single hour of their own subjective experience might correspond to decades or even centuries, passing for those watching from a safe distance. They would, in a very real sense, be traveling into the future. Upon returning to their home planet, they would find it utterly transformed, a world they no longer recognize while they themselves have barely aged. This is the ultimate expression of the twin paradox from special relativity, but amplified to an almost unimaginable degree by the crushing gravity of the singularity. We use atomic clocks to build the precise mathematical models for these mind-bending scenarios. These clocks provide the experimental bedrock, the proven reality of time dilation, that allows physicists to confidently extrapolate and explore these extreme theoretical landscapes. They are the tangible proof that the rules governing such fantastic journeys are the very same rules that affect our GPS satellites every single day. While building a functional time machine remains firmly in the realm of science fiction, the act of studying these effects is anything but frivolous. It pushes our understanding of general relativity to its absolute breaking point, forcing us to ask profound questions about causality, the nature of the universe's timeline, and whether there are any fundamental limits to time's elasticity. The atomic clock, with its unwavering quantum rhythm, is the key that allows us to ask these questions not as fantasy, but as serious physics, testing the very fabric of reality against the most extreme conditions the cosmos can devise. This synchronization would not be a signal in the traditional sense, but a gentle, universal tuning of reality's rhythm. It suggests that a cataclysm occurring a billion light-years away, like the collision of two black holes, does not merely send out a gravitational wave that momentarily stretches space. It might also send a subtle, persistent shift in the very rate at which time flows everywhere. This shift would be immeasurably small, a change so tiny that only our most advanced instruments could even dream of detecting it. But if it exists, it would mean the universe is constantly fine-tuning itself, aligning the ticks of distant clocks through the medium of spacetime itself. This is the grand idea of cosmic synchronization, a hidden harmony written into the fabric of existence. Our atomic clocks are the first instruments sensitive enough to even consider listening for this chorus. By monitoring networks of these clocks spread across the globe, scientists are not just keeping time, they are listening for a specific kind of pattern. They are searching for a synchronous drift, a moment when all the clocks, regardless of their location or design, suddenly and minutely change their tick rate in perfect unison. This would be a signature that cannot be explained by any local phenomenon, not by earthquakes or atmospheric changes or solar flares. The only explanation would be a global event, a ripple through the cosmos that has reached out and touched every single clock at once, tuning them all to a new, universal tempo. Finding such a pattern would be one of the most profound discoveries in the history of science. It would reveal that the universe is not just a collection of isolated objects governed by the same laws, but a deeply interconnected system, a single entity where an event in one corner can whisper a change to every other corner simultaneously. The precise ticking of an atom in a lab and the violent merger of black holes in the void would be linked by an invisible thread, two participants in a cosmic dance of unimaginable scale. This profound connection transforms how we learn about the universe. Suddenly, The most abstract ideas in physics are no longer confined to dense textbooks or complex equations. They become tangible, something we can measure and even use. A teacher explaining Einstein's theory of relativity can now point to a real device, an atomic clock, and describe its daily dance with gravity. They can show how the same principle that makes a clock on a mountain run fast also dictates the bizarre fate of an object falling into a black hole. This is not a distant theoretical concept. It is a working reality that powers the phone in a student's pocket. By grounding these colossal cosmic ideas in a relatable, human-scale technology, education becomes a journey of discovery. Students are not just memorizing facts, they are connecting the dots between the quantum world inside an atom and the vast gravitational empires ruled by black holes. They see that the universe operates by a consistent, if strange, set of rules, and that humanity has found a way to listen to its whispers. This approach does more than just convey information. It sparks wonder. It inspires the next generation of physicists, engineers, and dreamers to ask the next great questions, to build even more precise clocks, and to look at the night sky not as a collection of distant points of light, but as a dynamic, interconnected system waiting to be understood. The classroom becomes a gateway, and the atomic clock becomes a key, unlocking a deeper appreciation for the hidden symphonies of the cosmos. These precise machines force us to confront a question that has puzzled philosophers for centuries. Is time an absolute river flowing at a constant rate for everyone and everything in the universe? Or is it a relational tapestry, its pace defined entirely by its local environment and the interactions within it? Our atomic clocks provide a powerful answer. Time is not a universal constant. It is a personal experience shaped by gravity and motion. A second for a clock on a satellite is not the same as a second for a clock on the ground. They are both valid, yet they are different. This relational view of time, confirmed by experiment, shatters the classical idea of a single master clock for the cosmos. It suggests that time itself might be an emergent property, a side effect of deeper relationships between objects and the fields they inhabit, rather than a fundamental stage upon which the universe performs. This perspective is humbling. It places our human experience of time's steady march into a much broader, more fluid context. The ticking of a clock, the aging of our bodies, the orbits of planets, these are all local phenomena, threads in a much larger and more variable fabric. When we use these clocks to measure the universe, we are not simply applying a rigid external ruler. We are engaging in a dialogue. We are using a local phenomenon to ask questions about a non-local reality, and in doing so, we are learning that our most intuitive perceptions are merely a small part of a much grander, more mysterious whole. These devices become more than tools. They become lenses through which we ponder existence itself, challenging us to see reality not as a collection of isolated things, but as a dynamic web of interconnected relationships where the very flow of time is a conversation between the observer and the cosmos. This beautiful convergence of fields is what makes the quest so powerful. It is not just physicists in isolation trying to decode the universe. It is a symphony of disciplines, each playing a critical part. Precision engineers and materials scientists work to create the perfectly stable environments for these clocks, developing new lasers and vacuum systems that push the boundaries of technology. Their work is a form of art, a meticulous craft dedicated to eliminating every possible source of interference, every whisper of vibration that could drown out the cosmic signal. Without their skill, the most brilliant theoretical idea would remain untestable. Meanwhile, astrophysicists provide the cosmic context. They use telescopes to observe the extreme environments around black holes, gathering the data that informs what the theorists are trying to explain. They are the cartographers of the unknown, mapping the territories we are trying to understand from afar. And the philosophers are there, too, grappling with the profound implications of what these discoveries mean for our understanding of reality, causality, and the nature of existence itself. This is not a side note, it is the engine of progress. When a clock designer explains a new technical limitation to a theorist, it can spark a completely new idea for an experiment. When an astronomer shares an anomalous observation from a distant quasar, it can send everyone back to their equations. This constant dialogue across traditional boundaries is how we break new ground. It proves that the biggest questions cannot be answered by a single field working alone. Understanding time requires the poet's sense of wonder, the engineer's relentless pragmatism, and the physicist's mathematical rigor, all working in concert. The atomic clock is more than a scientific instrument. It is a meeting point, a place where different ways of seeing the world come together to listen, as one, to the heartbeat of the cosmos. Hollywood paints black holes as cosmic vacuum cleaners and time travel as a thrilling adventure. This sensationalism captures our imagination, but it often obscures the profound, tangible reality of the science. The true story, the one told by the steady tick of an atomic clock, is far more fascinating. These devices offer a powerful antidote to exaggeration by grounding the universe's greatest mysteries in something we can all understand: precise measurement. When we talk about a clock on a satellite gaining microseconds, we are not dealing in speculative fiction. We are discussing a daily, practical truth that makes modern life possible. This shift from the sensational to the factual is crucial for building real scientific literacy. It transforms black holes from monstrous abstractions into extreme examples of the same gravitational rules that affect a clock in a lab. By focusing on the real-world experiments, like the jetliner flights or the clocks on a table, we invite everyone into the conversation. We replace fear of the unknown with the excitement of discovery. This is not about dumbing down the science. It is about smartening up the dialogue, showing that everyone can grasp the fundamentals of how our universe operates. The goal is to replace the question, what if, with the far more powerful question, how do we know? That is how we build lasting enthusiasm, not for science fiction, but for the breathtaking science fact that is unfolding all around us, measured one perfect atomic tick at a time. But this incredible pursuit of knowledge does not happen in a vacuum. Every leap in precision, every new underground lab or space-based clock, requires a tremendous investment of resources and human ingenuity. This naturally leads to a vital question. In a world facing urgent challenges from climate change to disease, how do we justify the allocation of significant funds and brilliant minds to measure the seemingly imperceptible drift of time? The answer lies in the unforeseen returns of fundamental research. The very same quantum techniques that stabilize an atomic clock are now driving revolutions in computing and secure communication. The exquisite control over individual atoms is a technology that spills over into medicine, materials science, and engineering in ways we cannot always predict. This research is not a diversion from solving Earth's problems. It is an investment in the foundational tools that will empower us to solve them. Furthermore, we must consider the potential for dual use. A clock sensitive enough to map underground resources with pinpoint accuracy could also be used to locate hidden military installations. A network of clocks that can detect the subtle tremors of an earthquake hours in advance could, in theory, be repurposed. The scientific community must therefore navigate this path with a strong ethical compass, championing open collaboration for peaceful purposes while safeguarding against misuse. This is the practical reality of exploring the cosmos from a lab bench. it is a reminder that science is a deeply human endeavor, woven into the fabric of our society, reflecting our highest aspirations and our most complex challenges. The quest to understand a black hole's whisper is not just about physics. It is about who we are, what we value, and what kind of future we choose to build with the profound knowledge we uncover. This global conversation requires a global ear, a network of listeners tuned to the same perfect rhythm. International projects are now linking the world's most precise atomic clocks into a single, planet-sized observatory. This is not a solitary endeavor. It is a collective human effort to hear the universe's quietest whispers. Initiatives like a potential global atomic clock network synchronize these exquisite instruments across continents, from deep mines in Europe to isolated labs in North America and mountaintops in Asia. By comparing their ticks across vast distances, scientists can filter out local noise like seismic activity or atmospheric changes to search for signals that affect every clock simultaneously. This is the ultimate test, a way to distinguish a passing truck from a ripple in spacetime itself. These collaborations do more than just share data. They pool brilliant minds and immense resources, accelerating the pace of discovery in a field where progress is measured in increments of almost unimaginable precision. A breakthrough in a Japanese lab can instantly inform an experiment in a German facility, creating a feedback loop of innovation and insight. This united front is essential for tackling the grand challenges of modern physics. No single nation, no single institution can build the tools to find quantum gravity alone. It requires a global community, united by a shared curiosity about the fundamental nature of reality, each member listening intently for their part in the cosmic chorus. This magnetic pull toward the unknown is irresistible to a new generation of scientists. They are not just reading about these ideas in textbooks, they are building the tools to test them. The mysterious synchronicity between a cosmic monster and a lab instrument has become a beacon, guiding entire research programs toward a single, profound goal. To hear the universe's quietest note, this quest demands clocks of almost impossible precision, devices so stable they can measure gravitational shifts smaller than those caused by a single cloud passing overhead. It pushes engineers to master the quantum world, to control individual atoms with lasers and magnetic fields, all in service of creating a more perfect vibration. Each incremental improvement is a victory, a step closer to a device that might finally detect the faintest tremor from a distant void, but the inspiration flows both ways. The theoretical challenge of understanding a black hole forces physicists to refine their ideas about quantum gravity, to develop new mathematics that can describe both the smooth fabric of spacetime and the fuzzy grain of the quantum world. They use the precise data from atomic clocks to stress-test their equations, looking for any crack where new physics might hide. This beautiful feedback loop between theory and experiment, between the immense and the infinitesimal, is where the next great discovery will almost certainly be born. It is a frontier that welcomes anyone with curiosity, drawing in young minds eager to contribute their piece to the grand puzzle. Their sustained passion, this relentless drive to understand, is what will carry this exploration forward, ensuring that our map of reality continues to expand into the deepest mysteries of space and time. Yet a persistent myth portrays black holes as cosmic vacuum cleaners, actively sucking in everything around them, including time itself. This is a fundamental misunderstanding of how gravity works. A black hole does not pull on time like a pump pulling water. Instead, its immense mass creates a deep valley in the fabric of spacetime. Time does not flow into the hole, it simply slows down as the gravitational slope becomes steeper. It is the difference between a river being actively pumped away and a river flowing naturally down a hill into a deep basin. The black hole is the basin, not the pump. This distinction is crucial because it changes our view from an active, almost malevolent force to a passive, geometric consequence of mass. Similarly, the idea that atomic clocks are immune to gravity because of their quantum precision is another common error. Their incredible stability is precisely what makes them so susceptible to gravity's influence. They are not imperfect mechanical clocks whose flaws mask subtle effects. They are perfect enough to reveal those effects. If a grandfather clock is a blunt ruler, an atomic clock is a microscope that can see the individual grains of wood. It is this hypersensitivity that allows them to measure the warping of time, not an immunity to it. Another misconception is that these effects are too small to matter in our daily lives, confined to the realms of astrophysics and high-level research. But every time you use a GPS navigation app, you are directly interacting with a system that must account for both special and general relativistic time dilation. The satellites above us are literally older than they would have been if they had stayed on Earth, by a tiny but critically important fraction of a second. If engineers did not deliberately slow down the clocks on those satellites before launch, your map would be wrong by kilometers within minutes. This is not abstract physics, it is applied engineering that works because we understand the true nature of gravity's relationship with time. By clearing away these fictional portrayals, we can better appreciate the elegant, measurable reality. The universe operates by a consistent set of rules, from the gentle gravity of our planet to the extreme depths of a black hole's domain, and our most precise instruments are finally allowing us to listen to its consistent, whispering tune. This reliance on relativistic timekeeping is not a mere technical footnote. It is the absolute foundation of the global positioning system. Every single GPS satellite orbiting high above the Earth carries multiple atomic clocks on board. Their job is to continuously broadcast the exact time, along with their precise location. Your phone or car's GPS receiver picks up these signals from several satellites at once. Since the signals travel at the speed of light, your device can calculate its exact position on Earth by measuring the minuscule differences in how long each signal took to arrive. It is a continuous, high-stakes triangulation based entirely on the precise measurement of time. But here is the crucial part. The atomic clocks on those satellites are flying through a different region of spacetime than your phone on the ground. According to Einstein, two effects are constantly at play. First, special relativity says that because the satellites are moving at high orbital speeds, their clocks should run slower relative to clocks on Earth. Second, general relativity says that because they are farther from Earth's gravitational pull, their clocks should run faster. These two effects do not cancel each other out. The gravitational effect wins, meaning the satellite clocks gain about 38 millionths of a second every single day. That might sound tiny, but at the speed of light, that error translates into a positioning mistake of over 6 miles per day. Without the built-in software that constantly corrects for Einstein's predictions, your map application would be utterly useless within minutes. Your navigation system is, therefore, a daily and practical application of relativity, a technology that only works because we understand how black holes warp time. This is not abstract physics, it is in your pocket right now. As we look to the future, this principle becomes even more critical. Navigating a spacecraft near a massive planet like Jupiter, with its immense gravity, would require even more precise time dilation corrections. And looking even further, one can imagine a future where spacecraft might use the predictable time warping around a gravitational extreme as a kind of cosmic lighthouse. By measuring the subtle shifts in the tick rate of an onboard atomic clock, a ship could infer its position relative to a neutron star or even a black hole, using the gravity well itself as a navigational marker. The same physics that makes these objects so destructive could one day become the guideposts for the most ambitious journeys through the cosmos. Yet for all we have learned, we stand only at the very edge of this mystery. Our current understanding of this synchronicity is merely a starting point, a first glimpse into a much deeper conversation between the cosmos and the quantum. How does the immense gravity of a black hole truly influence time at the smallest scales, where the fuzzy rules of quantum mechanics take over? Could the chaotic quantum foam at the event horizon leave a faint imprint on the flow of time that ripples across the universe? These are not simple questions, and we do not yet have the answers. We also wonder if our earthly clocks could ever tell us something direct about a black hole itself. Can the precise tick of an atom here on Earth ever reveal the spin, the mass, or the temperature of a singularity millions of light years away? Right now, that seems like a distant dream, a whisper too faint to hear over the noise of our own world. But it is precisely these unanswered questions that fuel the entire scientific endeavor. They are not in points but invitations. They remind us that every discovery opens the door to a dozen new mysteries, and that the map of reality is still mostly blank, waiting for the next curious mind to fill it in. This ongoing journey, this relentless pursuit of a deeper truth, is what makes science so profoundly human. We are driven by the potential for a breakthrough that could arrive tomorrow, or in 100 years, a single observation that suddenly makes everything click into place and reveals the universe's final, hidden secret. From the quantum vibrations of a single atom to the immense gravity of a cosmic singularity, we have traced a single, unbroken thread. This is the profound synchronicity that governs our reality, a hidden conversation between the very small and the very large, all speaking the language of time. It reveals a universe that is deeply interconnected, where the same rules apply in a lab on Earth and at the edge of a black hole. This journey is a testament to the power of human curiosity, to our relentless drive to measure, to question, and to understand the cosmos we are a part of. Every tick of an atomic clock is more than a measurement. It is an echo of the universe's deepest mysteries, a reminder that we are now listening to a conversation that has been going on since the beginning of time. We would love to hear what surprised you most about this cosmic connection. Share your thoughts in the comments below, and if you enjoyed this exploration, subscribe for more journeys into the heart of space's greatest mysteries. Never stop looking up and never stop wondering, because the universe always has one more secret to reveal.